Hello everyone, I will be teaching this second session in the class. This will be one of the two sessions I will be teaching for mostly administrative reasons. I will only teach two of the sessions, but we'll see how it goes. Alright, so in the first session, Olivier talked to you about a different sort of approach to morphology, which is this abstractive idea, which is most commonly known for the word and paradigm morphology, and how it contrasts with constructive morphology. There are several advantages to abstractive approaches. For me personally, one of the most interesting bits of it is that it makes quantitative and computational work much easier than what you have in constructive morphology. In constructive morphology, it is extremely difficult to do quantitative work with morphemes, or if you're doing paradigm function morphology, working with rules, inflectional rules, is also extremely difficult. And I'm going to show you some things which are very easy to do if you work in an abstractive framework. Right, the aim of this class is to present to you some distributional properties of corpora and the lexicon. I will mostly look at the Zipfian distribution, but I am also going to show you another couple of interesting distributions. I want to show you that you can do a lot with publicly available resources, mostly corpora, and although the aim is not to teach you how to do this, it should hopefully encourage a couple of you to try yourselves and do this. This is very simple stuff, what I'm going to be showing you, but you can always go more complex. So this is the basis, the foundation. This sort of, it's not a tutorial, but this class, I'm using R, and I'm showing you all the R code to generate the plots that I am going to show you. I want to emphasize that you do not need to learn R, you do not need to know R or learn how to code or know any programming to follow. I want to show you this in case anyone feels interested to do something similar, and maybe to encourage you that you should do, in fact, learn at some point, maybe not for this class, but later on, how to program. It is a very useful tool to have if you do not know any programming, and after this class you're interested. I find this particular course here extremely good and easy to follow, and it's free, and it teaches you basically everything you need to know to start working with R, but you don't have to, just if you want. Okay, now to the datasets I'll be using initially. These are the universal dependencies. I don't know if any of you have heard of it. By now they are quite famous and quite popular, mostly for typological work. This is an effort to standardize dependency parsing for making dependency tree banks for different languages. So the idea is that one unified annotation system can be used for any language you want. And the website is here, and you can see the resources that they have available. They have quite a few languages by now. Most of them have relatively few words, a small corpora with under 1,000 words, but some of them are quite large. Particularly German, it's extremely large for a tree bank, at least. And for the small ones, they are still interesting, like the Hittite or the Coptic corpora. Those can be quite interesting. And it's very useful because since the annotation is homogeneous, it's very easy to do cross-linguistic comparisons without having to deal with different types of annotations of different corpora. So that's the resource I will be using at first. Then later on I will be using some homemade lexical resources, but I am also going to show you some freely available lexical resources. Right, and this first step here, I'm not going to talk about it too much, because this is just something you need to do if you want to follow. Basically, you need to load some libraries to working with universal dependencies, and then you have to load up the universal dependencies and build a corpus. This basically is just building a corpus, joining together all the individual sub-languages we have in universal dependencies. And this is this object here. And then we write it to a file, and then we read it as a corpus. So this object, if you see it later on, it's the corpus of all universal dependency tree banks put together. Right, that's just the beginning, the pre-processing. And how do universal dependencies look like? The format is like a table, and the table is quite large, so it's decomposed into several lines of columns. But here are the first 3 columns. Here we're seeing only 6 rows, and we have first a document ID. In this case, it is empty. So this is this NA, that means that it is empty, no value. Then we have a paragraph ID. In this case, it's the paragraph 0, and then a sentence ID within the paragraph. The ID is def s1. Then we have a column with the sentence. If you haven't seen what language this is, then try to guess. And then we have the actual annotation of the sentence, and the annotation has the following columns. First, we have a token ID, and this token ID is sorted linearly. So 1 for the first word in the sentence, 2 for the second word in the sentence, 3 for the third, etc. Then we have the token, and the token is the actual word that you see in the sentence. So here is the sentence. The first token is N, then ons, then hop. I can't pronounce it, but you can see it. Then there's the lemma. They use mostly automatic lemmatizers, but sometimes they annotate it by hand. I think that for these Africans, the corpus, they did it by hand, but I'm not sure. Then you have the universal pause part of speech annotation. This is also a standardized part of speech annotation, which can be used for any language that they've implemented. This tells you the parts of speech of each of the tokens. So here you see the hop is a verb. Then you have a simplified pause tag. This is less standardized and not very useful. After that, you have a column which sometimes have values, sometimes doesn't, with the morphological annotation. You see, for the first word we don't have a value, for the 6th word we also don't have a value, but the 4th words here do have morphological annotations. Particularly here, it gives you quite a bit. So it gives you the subcategorization, the tense, and the verb form. Similarly for the pronouns, which is an accusative or nominative, it's plural, it's first person, and I think this is a personal pronoun, I'm not sure. Then the next column gives you the position or the token ID of the head. The head is what governs something else. In this case, we see that the verb is the root in the corpus, That's why it has here a 0, because it's the head of everything else. And you also see that the first two words have as a head the verb. They depend directly from the verb. It also gives you the dependency relation. This is an adjectival modifier, if I am not mistaken. This is a nominal subject. You see here, this is the root, and then this is a determiner, and its head is the fifth token here. So this here D is determiner from here, not sure. And the next two columns are still not used by the universal dependency tree banks, these depths and misc. And then here I have some columns which I inputted while creating the corpus, which is it tells you what corpus we're using and what language. And corpus, because in the universal dependencies for many languages, let's see your favorite language ever, Russian. You see we have 4 different corpora. So that's what this column is doing in any case. Okay, so we can start by doing the most basic thing you can think of, which is basically to count the words in each corpus. You can see them here, but it tells you here, but let's do it anyways. So we're just grouping by corpus by language. So we want to count the words by each language and aggregating over corpora and then print them. And this is the result. It's a table and it's organized alphabetically. There is nothing interesting to see if organized this way. You do see that the largest corpora like Czech and German and French have at least 1 million words, but many corpora are very small, like Assyrian, it's only 400 words. But it's there. And just looking at it, there's nothing interesting going on. So let's move on to the Zipf distribution, which is the main topic of this class. Now, I don't know if you've heard of this before. The Zipf distribution is a power law distribution, and in its theoretical form, the idea is that the most frequent word in a corpus will have frequency x, and the second most frequent element will have a frequency of x divided by 2, the rank, so the second one, so divided by 2, the third one will be x divided by 3, and so on. Here we're starting with a frequency of the 100,000, and we're creating the theoretical distribution with this formula. As I told you, frequency or maximum frequency divided by rank. Again, it doesn't matter if you don't understand this formula, it's just if you want to replicate it and play with it later, then you can come back to it. I will make all this code available, or you can pause the video, however you prefer. So if we plot a theoretical Zipfian distribution starting in 100,000, we get this plot, and we're organizing them by rank. So the first one has 100,000 items, the second one 50,000, third one 33,000, and so on. And you see that the frequency drops off very quickly. Very few items have a very high frequency, and many items have a very low frequency. And this is the main point about the Zipfian distribution. This asymmetry between the frequency of the most frequent items and the frequency of the tail items. Now, if we plot a Zipfian distributed corpus in a log-log plot, we should get a perfect line. I will use these log-log plots over this rank to frequency plots later, because in the ranks to frequency plots it's very difficult to see anything for the tail, as you can see. However, in the log-log plot, then you do see quite nicely that there is a line. We can generalize the Zipfian distribution a little bit better. Namely, we can add a shape or a slope parameter and the slope parameter controls how fast the frequency drops. In the previous Zipf distribution, this slope parameter was 1, so we don't have to write it, but we can modify the slope parameter as we want. In this case, I am going to show you what happens if we start with a frequency of 1000 and 10 different values for the slope parameter. In this case, it's SS here. We plot it, and this is what you get. You can see that as the S parameter increases, then the frequency drop-off gets faster and faster and faster. But crucially, you always get a line. And this is also kind of the point. However, these are theoretical Zipf distributions. It is rather rare that you find perfect lines in nature. So let's look at what happens in practice. For very obvious reasons, I will start with French. So we take from the corpus, we compile with all languages, just the version or just the corpora for French. And you can go to universal dependencies, look for French, and you have it here, and you see that there are 3, 4, 5, 6, 7, 8 corpora for French. This one I think is still not done, so we probably only have this corpora here. Now we can count how many words we have. In this case, I am removing all words which do not have a lemma. You'll see why in a bit. And if we count the number of words with a lemma, you get slightly over 500,000 words. Now, we can start by looking at what happens with the most frequent lemmas in the corpus. And here they are. This is maybe something that you've already seen. It's not very shocking. The most frequent lemmas are function words and the verb to be and some punctuation marks, because this is what's mostly used. And if we do the same one, the same thing, but instead of using lemma, we use token frequency, so the actual words, we get what's virtually the same result. You get some function words, some punctuation, articles, and the verb to be. I think that is the verb to be in any case. Now we can plot the distribution of their frequency and see what happens here. I'm taking the 100 most frequent lemmas, and we plot their distribution, and you see we get what's very close to being a Zipf distribution, with the most frequent one very frequent, then the second one is almost half its frequency, and so on. We can of course also do it by actual word form, and you get also something that's very Zipf-like, maybe a little bit less Zipf-like at the beginning, but the tail does quickly become Zipf. We can also do this log by log plots. In this case, it's log frequency by position, and you see that we get what approximately a line. And this is for lemmas, this is for actual tokens or words, and we also get approximately a line. And especially after this point, it becomes very quickly linear. Now, there are many other things we can look at. For example, you may be interested or think this is just a coincidence. So maybe verbs behave differently. Well, here I am just looking at the verbs in the French corpus and the token frequency. I am taking the 100 most frequent verbs, and what we see is again Here is the log frequency by log position, and you get almost a perfect line. If we look at nouns, we get what's essentially the same result. It is almost a line, not perfectly, but it's very close. We can explore different things. Say, within verbs, we want to see what the distribution is of different verb forms, and luckily the UD corpus annotates for verb forms. Here are some examples of verbs, and you see there. So these are different sentences, as you can see. This is one sentence. This is another sentence. I am just looking at the verbs and how they are annotated within these sentences. You see here the verbs, and you can see the morphological annotation. So we see we get the actual cells for the verbs, and we can just extract this and do as before, and have a representation of the verb cell distribution in the corpus. And this is log or log versus position, and you see what's very close to a line. These are the cells, and this is very important. I'll come back to it later. This makes certain type of work using corpora very difficult, because the most frequent or most of the frequency goes to the most frequent ones, while the least frequent ones have very low frequency. So exploring low frequency phenomena in corpora is very difficult, and it can require very large data sets. And even then, if what you're studying is really not frequent enough, then it doesn't matter how large your data set is, you're never going to have enough data. But so that's something to keep in mind when choosing what kind of phenomenon you want to work on. So don't choose something that's very low frequency, because working or doing corpus work with it is going to be very, very difficult. Now to this effort principle, if we go quickly back to what we had before, here the most frequent words, you can see that they are very short, mostly. Even though French doesn't have a very transparent orthography, these are phonologically short and orthographically short. So we can look at what's going on there, and the idea is that more frequent words are going to be more, or are going to be shorter. We can plot token length in characters, in orthographic length, by token frequency, and this is what we get. We basically see that the shorter items, or the more frequent items, have very small token frequency. Single token elements aren't as frequent, so this the causation is only in one direction. Shortness doesn't guarantee you that you're going to be very frequent, but being very frequent does guarantee you that you're going to be very short. We can also plot this in an unaggregated manner for the most frequent 1000 elements, and you see exactly the same thing. Yeah. And if we do this log plot, and by size we represent the token length, we get something that's sort of linear for the first 100, and if we take more, then the trend becomes even more and more linear. Here's for the first 1000 items in the corpus, and if we take 10,000 items, the trend's even more linear. So as I keep adding items of lower and lower frequencies, I keep getting longer and longer items. Here we go up to 20, here only up to 16, and here only up to 7.5. The explanation for this that Sip gave is that people are lazy, and if you repeat something very often, or you know that you have to repeat it very often, then things are going to start getting shorter. This explanation is not necessarily universally accepted. Some people, I don't know if you know how Martin Haspermat, he's argued that it doesn't really work like this. It's rather about what you expect to hear. So it's not that people are lazy because they repeat something very often, but that people are lazy because things which are very expected don't need to be pronounced with as much detail, so they start to become shorter. There is no consensus, but the fact is that it's quite clear that more frequent elements are shorter. Yes. Okay, so now to the paradigms. Here we're looking at the paradigms, and we want to count how many verbs in French can fill their paradigm completely. So whether a verb appears in all its possible inflection cells, at least the ones present in the corpus. For this sort of work, this corpus is very large, as Olivier might have told you about his work on Czech, but we can still look at it. Here are some verbs, and we can count how many different cells for verbs in French we find in the corpus, and the answer is 97. Here are some of them. You can take a look. Hopefully this tells you something. It's quite a few, and this is too much for just a showcase, so I am going to show you only finite forms. So we're only looking at verbs in finite forms, and this is what we get. And the total number of finite forms in the corpus is 63. Now we want to see how many total forms each verb appears in with. I think that's how you say that. In any case, so let's take a look, and we order it by how many cells they appear with. And here you have avoir, and this appears with the most different cells, or in the most many different inflections, and slightly over 25. This is not very much, considering that we, as we saw, we have 63 finite forms present in the corpus, so no single verb appears inflected for all forms. And for the rest of the verbs, it's even worse. They appear with even fewer forms. This corpus is relatively small to show you this very convincingly, but this is an absolute truth of corpora and morphology. You never ever see all inflected forms for nouns or verbs or adjectives in a corpus. That never happens. The low frequency items will never have all their forms realized. In languages like Finnish, with hundreds and hundreds of possible inflections, that's even worse. But even with something like just finite forms from French, in a relatively large tree bank, you cannot find all the inflected forms for any verb. So this ties to something that you're going to learn about later, which is called the paradigm set-field problem, which is how, if most verbs never appear with all their inflection forms, how do you actually deduce them as a speaker? Right, so corpus size and vocabulary size. This is about how the number of different items behaves with respect to corpus size. Very naively, one would think that if I double the size of my corpus, then I should double the size of my vocabulary, but this is not the case. So we're going to look at German. This is an example of the structure. We have over 3 million words in this corpus. It's the largest one in the universal dependencies, and what we want to do is see how many different words we have at different sizes of vocabulary. And what I'm doing here is creating different sized corpus of 100 words and 34,595 words, 69,089 words, etc. And all the way till the maximum size of 3 million and something words. So we build the corpus and the different corpora, and then we count the different numbers of unique lemmas, and this is what we get. So this is the corpus size, this is the maximum, and this is the number of unique lemmas. And here what you can see is that as you increase the size of the corpus, you monotonically increase the size, the number of unique lemmas. However, the relation is not linear. At the beginning, the vocabulary size increases very quickly, and you can see that if you want to double the number of unique lemmas, so if you want to go to from 25,000 to 50,000, you have to more than double the size of the corpus. But to go from 1 million, from 50,000 to 100,000, then now the difference is much larger. Yeah. I hope this is sort of clear. So adding more words to your corpus will give you more different lemmas, but slower and slower and slower. And this should be very intuitive, because, well, you already have plenty of different lemmas here, and as you keep adding words to get new lemmas, you need low frequency lemmas, but low frequency lemmas will only appear in very, very large corpora. So you need more and more words to keep increasing the vocabulary size. We can plot this into in a log scale, and we get this practically a line. So the theoretical distribution of this should be a perfect line, and this is the empirical distribution, and it's almost a perfect line. It is not perfect, but it's very close to it. And this is now as Herdan or Heap's law. And this can be tricky, and it shows that it's not trivial to do corpus morphology. It's not extremely difficult, but there are some pitfalls. The pitfalls are mostly related to these two laws, Zipf's law and Herdan law, because they together mean that if you want to study low frequency phenomena, or you want very large vocabulary sizes, you need ginormous corpora. And this is one of the reasons they've been developing very, very large corpora, and why people have started building things like corpora from the web. This Corpus stuff from Berlin, maybe you've seen it, and those give you billions of words. We've also seen so far that very few items account for most of the frequency in the corpus. We've seen that it's impossible to fill paradigms, and very difficult to fill single paradigms. So it's impossible to fill them all. It's very difficult to fill the most frequent ones, though you can. With a large enough corpus, you would be able to fill the paradigms of certain verbs. It's just really, really hard. However, at the same time, I've shown you very simple scripts that show that doing corpus morphology is not terribly difficult, and we have already very good resources to work with. So maybe you're interested in this sort of work, and maybe you will look at some of these resources that I've shown you. Now, for a little bit of typology, I'm a morphologist and a typologist, so I like to look at different languages, and perhaps you think that just looking at French and German is really boring, and that's true. Just looking at French and German can be boring, so we want to look at different languages. And I'm going to show you a little bit of a meta joke, but it's real. It's not a joke, but it is a joke. This is the distribution of corpus sizes in the universal dependencies. So if you aggregate the number of words and then plot them based on the most frequent to the least frequent, you get essentially a Zipfian distribution. So corpus sizes in a repository like the universal dependencies repository follows a Zipfian distribution, which I think it's quite interesting. It also shows you that this is not a thing about language, but it's more about power laws in nature. But in any case, so I'm going to pick a few different languages. There's 9 languages: German, Russian, Japanese, Arabic, French, Estonian, English, Czech, and Finnish. And I want to show you that Zipf's law applies here as well as in French. Here are some examples of sentences from these different languages. And we now basically take the token frequency, the token frequency for these 9 languages, and we do the same log by log plots. And what you see is that for all 9 languages, we get what's essentially the same result. This sort of linear relation between the position or the rank of the word and its frequency. And this applies across the board. And you could ask now, well, does it apply across the board also for just verbs, for example? So here is the same plot, but now I'm not looking at all the tokens, but only at the verbs. And you see more or less the same thing. It's not identical. And now you see a few differences, but it's not much. And you can look now at nouns, also across languages, and again you see a few differences, but it's very, very similar. Now, what about different corpus sizes for different languages? As I mentioned before, we have different corpora for each language in the universal dependencies. For example, for Czech we have 5 corpora, for English we have 5 corpora, for Estonian we have 2. So we can ask whether the corpus size matters for Zipf. So I'm going to decompose the previous plots into different plots for different corpora, and that's what we have here. Same idea, but now each of these lines is a different corpus, and what you see is basically that it doesn't matter. For the different corpus sizes, the frequencies do what's essentially the same thing, which I think it's quite interesting. And now if we do it just by verb, we get the same result. Just by noun, we get the same result. And yeah, you see that the pattern is stable across languages. It's very similar. It's very stable across corpora and corpus sizes. So it's quite robust. There are some open questions. I haven't talked about this. So why is everything self-distributed? The quick answer is that we don't know. There's some speculation and some papers on the matter, but we don't yet have an answer. This basically concludes this first part of the lecture. See you in the next one.